The last family of power functions that we're going to talk about are the radical functions, which are power functions because we can write any radical, pth root of x, as x to the 1 over p. Again, we'll split up the even roots from the odd roots because they have different properties. And again, we'll start with the even roots. Even roots are functions of the form f of x equals the pth root of x, where p is even. And our example is f of x equals the square root of x. Now, this is another graph that we have not seen before, but remember that these functions are defined as inverses. If we sketch in the graph of y equals x squared, we can imagine reflecting that across the line y equals x to get the graph of the inverse. And then when we restricted the domain of x squared, that made the square root into a function. So what we're really seeing here in the graph of f of x equals the square root of x is half of a parabola that's lying on its side, which is a shape that we're familiar with. The domain of this function is the same as the range of the x squared function, so positive real numbers and 0. The range of this function is what we had to restrict the domain to. So also positive real numbers are 0. This function is one-to-one, and it has a perfectly good inverse, but that inverse has its domain restricted to make the inverse also one-to-one. Recall, this is why we risk introducing extraneous solutions when we take an even power of both sides of an equation to get rid of a radical. The square root function has no symmetry, and that's because the domain of f of negative x is different from the domain of f of x. That is, if we replace x by negative x, if we reflect across the y-axis, that changes the domain. We have a completely different function on our hands in that case. We don't have any asymptotes in this graph, but what we do have is this special point, 0, 0. It's an endpoint of the graph, so we have to pay careful attention to that when we're transforming this function. The second key point we'll use is typically going to be 1, 1 when we go to transform this graph. Okay, so that's even roots. Odd roots are a little bit less weird because we had to do a little bit less weird stuff to get them. So the odd root functions are of the form f of x is the pth root of x, where p is odd. And let's throw in the restriction that p is greater than 1, since the 1th root is really weird to talk about. It's not really a thing. Our example graph here is f of x is the 3rd root of x. And again, we can see that this is the graph of x to the 3rd reflected across the line y equals x, which is how we find the graph of an inverse. The domain of the pth root of x is just the range of x to the p, which when p is odd is all real numbers. The range of the pth root of x is just the domain of x to the p when p is odd, which is again all real numbers. And this function has an ordinary sort of inverse. No messing around, no domain restrictions, because the odd powers are 1 to 1. Because we don't have to mess around with the domain restrictions, these odd root functions are in fact odd functions. Right? It was strange that the even roots were not even functions, but the odd roots are in fact odd functions. We have no asymptotes for these positive pth roots. When we go to graph 1, we'll typically take as our key points -1, -1, 0, 0, and 1, 1. So fairly straightforward. Very similar, in fact, to graphing the corresponding power. Now, these are the last power functions we're really going to talk about here, even though we have this really big family of other power functions left over. If we have any rational power and we want to figure out the properties of that function, we're going to see it as a composition of some integer power with some radical, and use that to determine the properties.